So you're at Berkeley and you're doing a doctoral degree and you decide to work on distributed computing, which doesn't really exist as a branch yet. So A, what were you thinking? And B, we have a lot of professors and folks who work with students. If there's a person who's a student in university today and they're working on chip design systems, networking, storage, AI, what advice do you have for them?
Yeah, that's a great question. I I love programming, and I think that there's a real question on this today. What's the future of programming? I think the future for programming is bright, actually. And what this meant for me, I see how I fell in love with programming when I was 10 years old, well before I got to Berkeley. And so the real answer for why did I pick operating systems, which was the stand-in for distributed systems before distributed systems really existed as a field, was um, I looked around and I said, okay, where are the best programmers? Like the people who loved writing software, who are I'll put it bluntly, the hardest core hackers, where were they? Turn out compilers, but I didn't want to do compilers. So then what was number two? Operating systems. And so that's what I specialized there. Yep.
So I have the same background as you, systems and AI, and I did systems at Stanford pretty much because the professors were really interesting. And I felt you couldn't go wrong if you picked really interesting professors. But if you're a student at university today, are you going to be concerned about if AI is going to take away jobs? Is AI going to help you in your job? Like, what are you thinking if you're a student today?
So today, programming is way easier than it was when I was an undergraduate at some level. Way easier. Documentation's better, libraries better, open source is way better. You can find virtually any problem you want to solve, someone has solved it and has put it online. And compared to when I was an undergrad, there are probably 1,000x more programmers. So why is it that programming got so easy, quote unquote, relative to when I was an undergrad, and what we could create got so much more grand, and yet we have way more software engineers than ever before? By the way, same with hardware. It around the time I was an undergrad and by a grad student, a couple of people could go build a chip. And now we're building these incredible chips, and well, it takes hundreds, if not thousands of people to build a chip. I think the future is bright because as things get easier, the only thing that happens is our ambitions grow. Like it would have been unimaginable for us to build the chips and the software that we build today because it was so hard 30 years ago. It's gotten exponentially easier. Our ambitions have grown even exponentially more. So in my view, actually, things are going to continue in that trend. Yes, AI is going to make things easier. And that means that a lot of things that are super hard today, that take a lot of time, are going to get easier. We're not going to say, okay, now let's just maintain our ambitions and keep doing the same thing. We're actually going to raise our ambitions. And my prediction is there's going to be more engineers, not fewer.
I agree. Okay, so fast forward from grad school all the way to TPU V1 and V2. You're involved in the design of TPU. We're betting on specialized architecture and hardware. This is very anti-intuitive for what the wins are at the time. And yet you make a decision, a very costly decision that is obviously paid in spades over and over for Google. How do you make that decision? Tell me some interesting stories from that time.
Yeah, I think to be clear, a lot of people get credit for that, and more credit than me, for sure. I think that Google is built on data, and Google is also built on a portfolio model of investment, and I think this is key. So what I'll say is actually what allowed us to make this decision is that the leadership at the time, senior leadership of the company, and I try to carry this forward, it insisted that 10% of our staff, and we had relatively significant staff even back then, was working on things that have a very good chance of failing. That basically there would be people in the company who would say, why are you doing this? This is going to fail. And in fact, so if you say, I must have 10% of my staff working on something that could fail, then it's not a question of whether you take on something ambitious. It's a question of what ambitious things do you take on. And that is a really powerful enabler where you know that 10% of your portfolio, think of it if you're investing, right? 10% of your portfolio might be reserved for speculative, startups. You might not put 100%, maybe some of you would, but you probably wouldn't put 100% there. But if you know that it's reserved there, you're not going to compare the 10% there to, what your favorite safe stock is, or bond, or whatever. So now the ideas were actually pretty compelling around TPUs. Here's a use case with some very good backing that says people want to interact with computers via voice. That seemed pretty clear. The other one that was right behind it is people want to be able to interact with one another across the language barrier. Doing this kind of work was incredibly expensive. The fundamentals of the algorithms from a computation perspective were incredibly expensive. It just really made sense, is what I would say. So actually, if you're going to reserve 10% of your staff to work on something, I'll say it was a relatively easy decision. The hard decision was making sure that 10% of your staff were reserved to work on such hard things or speculative things rather than this one, because this one actually had a pretty clear case.
So follow the consumer use cases and reserve 10% of your staff for really risky, but, things that make sense.
Yeah, and
things that are promising.
we tell you about the ones that succeeded, right? And we don't tell you about the others that don't, but that's okay because that's the whole nature of the portfolio.
Okay, so then fast forward to 2023. I remember where I was when I first read about these optical circuit switches that we had developed, which I think is an incredibly beautiful thing. I know you were also involved in, designing the first intercore interconnects, and then now we're at these OCSs. How do you see, tell me something cool about these switches. Tell me something cool about this architecture.
Yeah, so historically in networking, the way that you transmit data from one point to another is you put a header at the front of every data packet. This header just has some bits in it. The bits say, here's where the data is going to go. Routers, the elements that forward the data, look at the first few bytes of a packet, electronically process them, put them through a routing table, and they figure out, okay, for this packet with this destination, here's where I'm going to send it. This is how things have been done in the internet since 1969, when the actually first 4 sites of the internet came on board. Over the decade, but this was counter to how everything was done actually in other places that leverage circuit switching, telecom. So there's actually been a longstanding idea of leveraging optical circuit switches that actually don't do any processing in the electrical domain. So what I want to say is, a little bit of background is required here. When you transmit data across the internet, you're probably going to go through 12, 13 on average hops. Each one of those hops is a router. But the connectivity between those two routers is optical fiber. So at each one of those hops, you have to convert the optics to electronics so that you can look at the packet header. Once you figure out where it's going, you then convert it back to optics. Very expensive, slow. We had this notion that for certain communication patterns, you could actually leverage optical circuit switching that was pre-configured for long flows, such as what you might have for machine learning training. And now the beautiful thing about these optical circuit switches that we deployed, didn't have a chance to go through it in the talk, is imagine that you could stick essentially 144 mirrors on a chip the size of my fingertip. And with microelectrical motors, you can rotate those mirrors in 3D, such that each of the routers is no longer doing electronic processing, but basically shining all the light down on these mirrors, such that the mirrors reflect light from input ports to the right output port with no electronic processing, no conversion to electronics, and essentially zero added latency. So you could create a programmable crossbar, and when you decide that you need to change your routing, you rotate the mirror very, very quickly, actually. So this was a controversial idea, very controversial idea, I would say. Billions of dollars were spent in trying to make it work. We were fortunate enough to come along probably at the right time to get it operational at Google. And it turned out to be key for the reliability requirements of OCSs as well.
And what's really cool is now you don't have to switch from electrical to optical back to electrical. And these are basically no latency because they're a speed of light.
That's right.
I think this is incredibly cool innovation that you all drove, and I found it personally very inspiring. Okay, so since you're talking about routers, let's switch to generative AI. One of the areas where I feel we as an industry in AI are underinvested is routing the right set of questions, the right intelligence to the right set of models. Yeah. And I know GPT-5 is supposed to be doing some routing, but I don't think it's gone very well. What are your thoughts on generally routing as like a key thing that we're not doing well in Gen AI today?
Yeah, and I think that you're absolutely right. This is my first order observation. I think that the mixture of experts that we have built into our models is a version of that. But I think to your point, it's still one model and we're doing routing within the one model, I think that there's huge opportunity for us to be able to specialize on individual queries. I gave an example of how for certain token prediction, it's easy. Like if your next token is probably you don't need a lot of horsepower to figure out that the next word is the. In other cases, it might be much more challenging. So what if we knew how hard a query is? And the fun part here actually is that you could imagine running a model on a query, a small model, that all it does is classify the hardness of the query and does forwarding, right, to the right model based on that. Now, I don't know how much I'm supposed to say here. It's a small audience. You can imagine that we are doing some of that at Google. In fact, Madhuri, you might be doing some of that yourself.
But I think this is one of those things we need to get right like immediately because orchestration is such a key part. And I think you said this in the talk inside as well. We have all the tools in these disparate places, but no one at all in the world yet has discovered how to put these together in ways that are like mind blowing and completely new.
Yes.
And I think that's something, this is one of those things that will unlock more use cases because it helps with latency, price, everything, especially for customers who don't have infinite money to spend on these kinds of models.
For sure. No, I think this is a hugely promising area, but I think to your point, it's also like almost guaranteed to happen. Not almost, I say it's guaranteed to happen.
Makes sense. Okay, one of the things I find fascinating about you is that you sit at the intersection of a lot of different industries that work at different paces. So data centers are very dependent on supply chain. And there really haven't been many supply chain innovations. And also, like, how much faster can you get something in a truck from point A to point B? There's like limited by, speed of road. Then you sit on systems design, which has like your 2-year cycles. And sometimes you do multiple architectures, you do one architecture. I know recently Elon announced they're only going to do one architecture at Grok. Great. And then you sit obviously with the AI systems because you do a lot of co-design with AI and systems to make systems super and hyper optimized for this AI. So how do you like balance this tension of 3 industries that are evolving at wildly different paces?
Yeah, it's a privilege, honestly. For me, it's a privilege. And I would say that actually, even for transportation, there's a lot of opportunity for innovation. In other words, if you look at the assumptions that we make for what it takes to get something from point A to point B, we have a lot of conventional wisdom built up. For example, I'll give a simple example. While you would never pay for air freights from point A to point B because it's way too expensive. I'll tell you with AI and the benefits that we get generation over generation, you actually would pay for air freight in some cases. So your version of routing is a really interesting thing here is, okay, what can I afford to put on a ship? That's the cheapest way. Like put it on a pallet. It's going to take a month. It's going to go across the ocean. What can I ship via air? What can I ship via train? What can I ship via truck? All these actually depends. I would say that there's some significant innovation in supply chain that can be delivered there. However, the most interesting part of it actually is power. So right now, the analogy I like to use is if you have 20 kilowatts in your home, that'd be pretty big. How much power do you think you're using at any point in time?
Peak or average?
Average.
3?
You're probably not using 3. You're probably using somewhere between 1 and 5%.
1 and 5% on 20 kilowatts.
Right. On average. You might peak, but the peak actually only happens if your refrigerator, if you've got a big refrigerator, kicks on. So the point here is data centers are not so different. Their provision, we don't do this, but still some people do. If you say, hey, here's a server and it takes a kilowatt, and now I've got 1,000 of them, so it must take a megawatt. What are the chances that actually all those servers are using a kilowatt at their peak simultaneously? Turns out it's 0. Like it's never happened in the history of humanity. So now why are you provisioning a megawatt and leaving a bunch of it idle? So there's actually, and AI computation is even more regular.
Yeah, cyclical.
And you can imagine that you would co-design your power and your computation in interesting ways. So I think that across the 3 industries, there's actually lots of opportunity for not having hard walls, but a continuous sort of stream of optimization.
Yeah, and I think it's really fascinating the opportunity you have to sit at the epicenter of those three and drive that innovation. So I'm really excited for you for that.
Appreciate it. It is a privilege. I mean, actually the only whatever secret weapon I have is I get to learn from the best across multiple fields, and just sort of integrate across it. I wish I had anything whatever bigger or than that. Yeah.
Okay, so let's talk now about the future. I think it's really difficult to foresee what's going to happen, hardware, AI, anything. But I guess I want to ask you about the role of self improvement. So, as models get smarter, I think we're going to see models design chips that work better for them, models that design better models. Say more about this.
Yeah. So the term here, in case you all haven't heard it, it is self-improving superintelligence, right? So SI squared, and this is the holy grail to some extent. And I think that we are seeing glimpses of this, Madhavi, right now.
Yeah.
And then if you look at some of the answers that are coming back to you from your favorite models, I know 2.5 Pro the best. It is doing versions of this where it's refining the answer in real time. We have a research effort that we actually recently published a paper on, joint with the GDM, called Co-Scientists. It essentially is at a place right now where for certain domains, it can generate hypotheses, scientific hypotheses, at par or ahead of leading scientists. The way it does this, it actually runs tournaments. So this is the self-improving superintelligence part. It actually generates hypotheses, generates many of them, and then creates a tournament where it pits one hypothesis against another, goes and does research, and picks a winner, and then does multiple rounds of this. The computation actually at this point can take many hours, even a day. But the output winning hypothesis through the self-improvement process is stunning, actually, in terms of its quality. So I think it's really interesting that 2 years ago, we were making, some of us, not me, but some of us were making fun of these models because they got things wrong so often. Now, why
Yeah,
is
like
it?
how many R's are in a strawberry?
I've used that joke. But the problem is the models were going left to right. They were doing next token prediction. Now, imagine that you are solving a hard mathematical proof problem, and all you could do was generate the next token. Well, let's also say, which I'm sure you all are, you're super smart. I bet you'd get the proof wrong most of the time. Like, people don't work left to right, they iterate. So the key insight for these models, which was only a couple of years ago that we were left to right,
Yes. Yeah.
we've now gotten to a place where we're no longer left to right. We actually say, oh my gosh, look, you know what? I wound up here. That makes no sense. Let me go back and figure out where I might have made a mistake. You do that. And if you get things right a lot as a result, the models are doing that now. So we have, I think, glimmers of self-improving superintelligence. These glimmers are going to get brighter and brighter.